Calculations of Entropy, lecture number 26. So last time we talked about the sort of the foundation of what entropy is and what it sort of means and how we can calculate any given compound's value for entropy. But now we're going to look at applying entropy to chemical reactions, and we're looking at changes in entropy. So when we do this, we're going to look at, since entropy is a state function, right, we can say that just like any other state function, the change in entropy can be calculated by the entropy at the final state minus the entropy at the initial state. So if we're doing a chemical reaction, that means that the sum of the entropy present in the products minus the sum of the entropy in the reactants is going to be the change in entropy that occurs. So we can calculate this in the same way we have enthalpy here, where we're looking at the change in entropy of the reaction is the sum of the entropy of the products minus the sum of the entropy of the reactants. Right? The same process we do. Again, we're going to look these up in a table, or they'll be given to you. But remember, entropy then is an absolute scale. We don't have that, unlike enthalpy, where we had this sort of arbitrary scale where we set the enthalpies of formation. The entropy values we can actually calculate using the microstate available. So all of these values for entropy are going to be positive. That doesn't mean that the changes in entropy will always be positive. It's just that each one of those values that we look up in the table will be positive. So let's look at an example. What is the standard enthalpy of change for the following reaction if it occurs at 25 degrees Celsius? So we're going to take carbon monoxide plus oxygen to give us carbon dioxide. Right? So the values are listed there. So we're going to take the change in entropy of this reaction is going to be the amount of entropy at the products, 2 times the entropy of CO2, minus the sum of the entropy of the reactants, 2 times the entropy of the carbon monoxide, plus the entropy of the oxygen. Again, here, there's no values that are 0, so each of these will have a value, and we can see doing it here that our value, we take 2 times the entropy of carbon dioxide, which gives us 427.2, minus the entropy of carbon monoxide, 2 times that, or 395.8, plus the oxygen, which is 205, gives us a total entropy change of a negative 173.6 joules per K. So notice also that these entropy values are on a much different scale than the enthalpy. When we talked about enthalpies, we always had units of kilojoules. Here in entropy, we're in units of joules per degree, or per Kelvin, excuse me, no degree. So there's a difference in scale. The enthalpies are we're talking about a much larger change in energy than in these entropies. But they're still similar. Right? But now taking what we know about entropy and how it's measured and some of its properties and this value, we can actually make predictions on what's going to happen in these changes in reactions just by looking at it, not necessarily doing the calculations. So if we look here, because the gas phase of the molecules have such large values of entropy compared to the liquids or the solids, we can make implications on chemical reactions by following the amount of gas present. Right? So in reactions where gas are either consumed or produced, we can make inferences on what that change in entropy is going to be. So if we produce more moles of gas than we started in products than we had in the reactants, we would say that in all cases this is going to give us a positive value in the change of entropy. If we decrease the total number of moles of gas in our chemical reaction, again, because those are such higher values of entropy, we're going to see that by decreasing that number, in all cases, we're going to see generally this decrease in entropy, or the entropy of the reaction is going to be a negative number. Right? If the number of gas molecules don't change, or if the change if there's no gas present, then we can't really make any broad pronouncements about the sign of entropy, but we will know that those changes will be relatively small. Right? Again, that's sort of a weird thing, what is small, but it's going to be a smaller number compared to when there are gas changes. But we can also, if we add more the possibility for rotations or more movement in the molecules, we will also see a positive change in entropy. That's a little harder to see at this point because we don't, a lot of times can't see what those molecules look like or don't know what those molecules look like. But that's also another way we can see. If we're adding the ability for those molecules to rotate, then we're going to get an increase in entropy. So let's look at this bottom example here. What is the sign of entropy change for the following reaction, where we take 2 zinc solid plus some oxygen gas to give us 2 zinc oxide solid? Again, if we're looking at this, we go from reactants where we have gas molecules to products where there are none. So the amount of gas molecules is going down. Therefore, we would say that this then delta S should be negative. The total amount of disorder is going to decrease in this reaction. And we said last time that enthalpy and entropy aren't directly linked, right? Or I guess they're different values, but they are in some sense linked because of the temperature idea. If we're transferring heat, typically we see a change in temperature. So when the temperature changes, we've seen also that this entropy value is going to change. So then we can sort of make some inferences about that as well, right? But remember, the system, we have to look at the relationship between the system and the surrounding. If we go back to our laws of thermodynamics, we said that the entropy of the universe is always increasing. So even when we're causing a reaction that causes a decrease in entropy, that because that law has to be true, then the universe itself has to overcome that decrease. Right? It has to be outweighed by a larger increase in the universe or the surroundings. Right? And we can make that emphasis because of this heat sink. The surroundings change are a heat sink. So when we see a decrease in surroundings, we get corresponding loss in. So in an exothermic reaction, the delta S of the surroundings has to be positive. In an endothermic reaction, the entropy has to be of the surroundings has to be a negative number. So they are in somewhat related, but not directly within the system, more of in the surroundings. So we can follow this. Again, a lot of words on this slide. We've gone through them sort of already. Then we said because the temperature and the entropy are linked, we can make these inferences. Right, so if we're following the amount of heat that's lost either as enthalpy or as Q, our surroundings, remember that our Q is going to be equal to N times the enthalpy, or delta H. So at constant pressure, and we're not changing many moles, then those two can be equal or approximately equal. So we can say that in general, when we're looking at the change in entropy of the surroundings is going to be equal to a negative change in enthalpy of our system divided by temperature, assuming we are keeping this at a constant pressure. So now in the next lecture, we're going to start putting enthalpy and entropy together in a new concept we call free energy.
Dad, I done did it.